Okay, hello everyone. Welcome to the second part of this stream, which I am trying to make a very simple epidemiology simulation that I've been previously created in Rust, and this time trying to make it multi-threaded in the sense that we could execute the simulation on multiple cores at the same time, trying to get greater speed increase. We're trying to get an even greater speed increase than what Rust just provides on a single core. We previously wrote a simulation both in Python and Rust, and we found that there was a dramatic difference from something to less than a second of execution time in Rust, it's 0.2 seconds, to an execution time of several seconds. Was it 12 seconds, 13 seconds in Python, given the same parameters? So we're simulating roughly 100,000 people. We are simulating precisely 100,000 people over 300 days, infecting each other and looking at sort of how a pathogen spreads in this population. This is a very simple toy simulation. It does not have clustering or probabilities or weights in any way. It does not have complex infection patterns or geography. It simply randomly picks another person to infect from a population, and then it will infect those people. And then they will go on to infect others and so on. So we have it's a very simple simulation, and it offers apparently some interesting questions for multitasking. I'm sure that these things have been elaborated academically and in epidemiology and programming related to that many times. So if you did look into the literature on this, I'm sure you'd find great solutions for the things we are struggling with now. But part of what we are doing here is to learn Rust. This is not so much about developing the simulation, because realistically much better simulations than this have been developed. So what we are doing here is just looking at how we program Rust. What we did last time, so we tried a couple of paradigms, or tried a couple of different ways to make this simulation multi-threaded. And the fundamental problem is that it has a very large vector of people structures, people objects. And any one of these people could go on to infect another person in the array. So it's not so easy to divide this array on threads that will execute. You will either have to provide a mutex or a RV-lock for the array itself or for the individual people inside. I have a feeling that there exists probably some beautiful mechanism to make this simulation run that's analogous to having this large array. Perhaps you don't actually need this large array to operate the simulation. And in fact, what we're trying to do in this currently in our attempt to make this multitask is what you're seeing on this slide. Or let's see, here we are. Instead of having one large array, we are now dividing the array on a number of workers, and we have one worker per thread that we are executing. And then we are providing channels where the threads will tell each other about people that have been infected, so that the thread that owns that person will then go on to deal with updating that person as the simulation days progress. We also saw that when we are doing it this way, we run into synchronization challenges. They're not difficult challenges, but they provide perhaps drawbacks. They provide limitations perhaps to how fast you can make this multi-threaded operation function. So basically, here's the thing: if you're on day 100 of the simulation and you want to pass information through channels to other workers about who got infected, then you have to make sure that those other workers are also on day 100. So they cannot fully run the simulation independently, at least not in the current paradigm. That means that you need to synchronize the threads at the beginning of the days and at the end. So you need to have them each thread figure out who to infect, and they need to pass those messages. Then when that is done, you need to make sure that all the threads get to the point where all the infections that they need to process are added, are sitting in a channel. These are buffered channels that they need to process those infections, and then once they are done, the simulation can tick to the next day. So you have 3 synchronization points. Actually 2. You have the beginning of the day. No, you have 3. The beginning of the day in the simulation. You have when the simulation has detected who gets to have an infection in the next day. And then you have the point where the threads have completed the work on infecting the individuals that they are responsible for. We implemented a solution to this in the previous stream using 3 channels. So we can actually have a look at them right now. We have a control. I can just explain it. We have a control channel that tells the threads what they are supposed to do and what task they should undertake. So the threads will read from this channel and wait to see what the next task is. Then we have a synchronization channel that goes the other way back to the simulation in the main thread. That's where the streams notify and put a Boolean true value into the stream when they are done. And then the simulation counts how many threads have it checked in. And the final thing is the infection channel. And the infection channel goes from thread to thread. So the simulation has a channel that goes into the threads that tell them what to do. The threads have a return channel that says back to the simulation when they have completed the current task. And then we have one channel that contains just the infections that needs to go into the threads people array. So that will contain the index or the ID of a number of people or a set of people that they need to post the infection in. So this synchronization, I think, causes us some problems. Perhaps it creates a lot of overhead. So I wonder when I look at this simulation as it is, whether there are certain scenarios where the multi-threading makes sense and certain scenarios where it does not. Because Rust is so fast, it may be that because there is so little activity happening on each thread, it might be that it is faster to not have multi-threading because of the overhead. But if there was a greater amount of work happening in each of these threads, then perhaps there would be more value in having a multi-threaded approach. It might also be that in the Python simulation, reality could be different. If the Python simulation took like 12-14 seconds to execute, in the same time that the Rust version took 0.2 seconds, which is mind-blowing, by the way. But then it might very well be that the execution time in the Python executable would benefit more from multi-threading than the one we have in Rust. So because the work, relatively speaking, takes longer in each thread in Python, unless the synchronization also takes longer. But in a 12-second run, I would assume that the synchronization overhead is relatively minimal. Okay. So I think we'll just get to the programming now. So again, this is a lot about my learning curve. So we might get stuck, we might get problems here, but I have a feeling we'll get this to run today. So we will copy the model from our 5th stream, and we will now be on our 6th. How about that? Stream number 6. So I'm just quickly going to check the stream's information, see that is correct. And it is. It was stream number 6. So we should be ready to go. So now I will be using CLion again, which is my favorite integrated development environment for us so far. There's probably a lot to be said for other ones too, but this is the one that I have started working on, and I do enjoy it. It provides a lot of pleasant functions and pleasant language tooling, and the tooling. And one of the best things about it is it shows these inline type hints that allows us to understand more about how the type system is operating and how it manages to infer these types as we go along. And it has, at least in the learning process, using CLion has been very beneficial because you can see the type hints directly in the editor when they are inferred, I mean. So it's not only the ones that you type in that you specify that you will see. You also see what the compiler thinks. Okay. So the simulation as it is now consists of the simulation object. We know how many people will be in the simulation. We have the actual simulations will now happen in the sim workers, which are threads, or these are objects that contain information about what goes on in that thread and what part of the simulation they have. And these contain the people array. These are the people that we are infecting. They also contain the total number of people in the simulation. We probably have to add some fields here in a moment. We also have a sim worker info object, which contains information about all the sim workers that have been created, and these are owned by the simulation. Again, this is Rust, so we have to think about ownership. So sim worker info is owned by the simulation, and sim workers are owned by their own threads, I guess, because you move, when we create them, we move those these objects into the enclosure, which means, I guess, that the thread now owns them for the duration of their execution, and then they should drop out of memory at the end there. They should be deallocated when the thread quits. So in the new function of okay, so basically just the main, so that we see how it gets started. We are opening the right files here. Yep. I'm just going to close the ones to the right because we don't need this. So basically what we are doing right now, and I can also just show the output of the simulation before we continue, just so if anyone new is joining, we can see what the output is. So when we look at the data coming out of the simulation, we see this very, very famous epidemiological curve, where the number of recovered people, that is the number of people that have had the condition, this is the same as counting people with the condition, because everyone survives in our simulation, except this curve is offset by a few days. So what you see is that in the beginning it grows very slowly, like it's sneaking up, and then it explodes and massively goes up, and then it flattens as people gain immunity against the condition. If you similarly look at the active infections, which is basically the rate of change on this curve, we get this beautiful almost Gaussian-like distribution here of the number of cases, and then it at the end it drops off. In our simulation, nobody dies. We are being nice. We say that there is no risk of mortality from this condition, but there's also no immunity, so a lot of people will have it. Okay, so what main does is that it creates a new simulation new. We say the number of people in the simulation, we say how many people we will see the infection in, and we have to create this method, or this we have to create this operation. And it says how many threads we will create. We're gonna drop this down to 6 threads now. It seems like we are inducing a lot of overhead by creating new threads, so we want to reduce that. Just running it without actually simulating took something in the vicinity of 40 milliseconds. It was a surprising amount of time just to run this for 300 days without the actual simulation, which tells me that there is overhead in the synchronization or the channels. My guess is that it's primarily in the synchronization between the threads. We then run it for the simulation with ask next day for 300 days. And then we finish. And finish collects collects all the threads, tells them to stop, and then joins them so that they go out of scope. And then in the end here, we will restore this later that will output the data that we just looked at, which was from a previous run of the non-multi-threaded version of the simulation. So each individual can have a susceptible, infected, or recovered state. When they are infected, they have a number of sick days, where either they infect no one, infect someone, or they conclude their clinical course. So let's say you have 14 days, the conclusion will be the last one, and then every 4th day, they infect someone along the way. So they'll have 3 days where nothing happens, and every 4th day they will infect someone. In total, they infect 3 people each. So the R0 would be 3 in this simulation. And again, the person has a clinical course, which is the vector of sick days. There's also a piece of information here that says what day of the simulation the person got infected. The reason we have this is because we try to optimize previously the way this works. So we right now we can ask the person object to get a status on any given day, and then it will calculate for us from the day infected versus the day that we are asking for the status on, either if the person is in the clinical what state the person is in on that day. So if it is person is susceptible to infection or recovered on that day, and then you have the option of a sick day being returned, meaning that perhaps the person is currently infected, and in that case you will get a sick day back. The problem is you cannot just start the simulation, ask for rate 300 immediately, because we don't know who gets infected. So you have to iteratively tick up day by day by day, so that you will complete the simulation. Otherwise, there would only be the 10 seeded people that would be infected on the 300th day as well, if you did not iterate every single day. The simulation now contains join handles, which are pointers basically to the threads that are executing. The worker infos, the ready receiver, which is a channel to check when the threads are ready. Channel contains a boolean. Total number of people in the simulation. We have an output table, which we can export to CSV at the end so that we get some data out. Thread control object control is an enum that gets sent down the control channel to each sim worker. The control receiver that tells them what to do in the next iteration. And they also have the infection receiver, which channel, which through that one they'll be informed which people have been infected this day, and that they need to cause the infection in. So they'll create a clinical course for those people. And yeah, that's effectively what we are doing in the beginning of the simulation. We just spawn our threads here. So we create the worker info and the actual worker, the sim worker, and then we spawn that into a thread. And we keep the handle to the execution, and then we are ready to go. So what we're going to do today is we need to look into what actually happens. So we need to dive into the sim workers, and we need to, when they get information that there is a new day, we need to have them loop through the list of individuals, and then we need to get a status for that individual on the given day. And then if that person infects someone, we need to look up what thread is responsible for that person that will then be infected. And then we will send that down the channel to that thread. And then we will loop like this, and hopefully we would get the same result as we did when the simulation was single threaded. With any luck, we're going to get a performance increase here, although my feeling again is that perhaps because of the synchronization, the gain will be minimal. It might be that this is not the case when you have a large number of individuals. So maybe we will try to see, we add to 1 million, 10 million, maybe up to 1 billion people is simulated, and then we'll see how it reacts. Okay, so let's move to the sim worker implementation. So right now, it will look for the control channel. It will ask for receive. Will not do error handling, so we'd simply do unwrap. And if we are told to get next day, then we will execute the next day function. If we are told to handle new infections in the infections channel, we will ask to handle infections. And then when we are done, we will just go finish equals true, and then it will drop out of this loop and drop off the edge, and our thread will close, and we are done. What we're going to do now is we're actually going to do the next day method. We already had this implemented in our simulation. We have it down here from the time when we were single threaded. I think we will simply take this method out, and then we will modify it to function in our new setting. So next day, here we are. Okay, so what happens on the next day? So we can actually add a comment here, because you should comment your code. Process next day of simulation. Okay, so previously we created this vector of new infections, and then we processed it at the end. I think we will take this one out. We will not update stats right now. We will perhaps do that eventually. We'll focus on what we will do in the simulation. So, okay, so what we previously did was that we got person objects out of ourselves. We asked an iterator, and then we filtered the iterator on the status on the current day. Okay, so get status on day is an I32 here. We can actually go here. This is not correct, and the reason for that is that we'll never have a negative day. So we can change that to an unsigned integer. Okay, let's go back again. So now we are on SimWorker. This file is getting rather long. We should probably think about popping this out into multiple modules now. Again, we already created 2 modules. We ran into a surprising problem with new modules, but I don't want to focus on that right now. So we are saying, okay, here we are. This is the next day. Now we are asking for an iterator. We filter and we ask for the people that are infected. The one problem we have here is that we are in this loop. We are asking for the status on the day, and that is a tuple containing the state and the option of a sick day. So the problem with that is that we are doing the same operation twice, which is not so good. So I think what we will do is we will get rid of this. We'll get rid of this filter, although it's a beautiful sort of mechanism. We will probably only want to ask for this update once. So instead, now we will do for person in self people, we will get the current day. Then we will check what the current day is. So we will ask for current day, like that. Then we, so now we are asking the person of the status on the current day, and the day is, for instance, 1, 2, 3, 4, and so on. So we will then ask if, basically we have two possibilities here. We can use the match expression. I like those. So we'll match current day. And current day will match the first field of current day. If you look at what it is the state. So this the second field, 1 here, is the option of a sick day, and that will only be valid if the person is infected. So the only situation where we want to progress now, we can fill out the match arms like this. If the person is infected, we don't want to continue go. Actually, an if statement is probably better here. Yeah, let's do that. We say if current day 0 equals state. So if it's not infected, we don't actually do anything with this individual. So if the person is not currently infected on this day, then we simply return, because we don't need to deal with this person. So this expression that we had here was what we were having this iterator before with the filter in it to get rid of. But because we need to call this function and it returns 2 pieces of information, it's probably better to only call this function once and do this instead of putting that in the filter function. The filter functions are very nice because they give you this they give you a new iterator that are filtering based on what you put into that enclosure, and that is cute. It's neat, like functional programming, or the same way you do it in TypeScript or JavaScript. It's lovely. Or I guess you can maybe also do the same in C# now, although they have link, which also is an excellent way of choosing things. Okay, so we have found that we will only pass forward in this function if we'll only process this person further if that person is infected. If the person is not infected, we simply return. Now we need to have a look. If the person is infected, then we do have a sick day. So we should be able to do this. For some reason we cannot. Yeah. So current day 1. Okay, if you do current day, we see that 1 is an option of a sick day. And we are just going to make the crazy assumption that our code just works. So we'll do unwrap to get rid of the error handling right here. And now we have 3 possible situations. Either today the person infects no one. If this is the case, we just let it go. We don't need to do anything more here. In fact, we don't need to return, because we will just run off the edge of the function here and return anyhow. And all these things will be released from memory instead of garbage collection. Rust will insert something here to get rid of temporary values, which is also kind of cool. Or actually, come to think about it, maybe these things will exist on the stack frame, and then that stack frame will pop out. Maybe that's how it's going to work here. If the person infects someone, we will get the ID of the person that person infects. So here, we need to add a mechanism that is different from the mechanism that we had before. We also have the conclusion, which is the final sick day. This was important in the previous version of the simulation, because we had another mechanism where we would, this array of sick days, we'd take one day off until we reach for every day until we reach the conclusion object, and then, or the conclusion state, and then we would take the final state out. And that is a nice touch, isn't it? It's simpler than the mechanism we are doing now. And then we would set the individual state using this one. But let's avoid for now this change. So we are now, what we need to do now is to deal with what happens if the person gets if the person infects someone else. In fact, what we can do is we can add the general match pattern here, because right now we don't care if the person doesn't infect anyone or if it is the day of the conclusion. So in all situations except if that person is sick and infects someone, then we will just go on. Now comes the next interesting question, since we are now multi-threaded. Now our array is split across multiple workers, multiple threads. So we need to figure out which thread is responsible for the infection for the person that we are going to infect, and then we need to inform that thread using a channel that person should now be infected. I see a couple of ways we could do this. One way is that the threads, all of them have access to, all of the threads would have access to information about all the other threads. We do have an array of sim workers, and we have an array of sim worker info. Actually, we don't have an array of sim workers because we move each sim worker into the thread, but we do have an array of sim worker info. And sim worker info, of course, has the ability to carry that information, because that has the channel that you put the infections into. The thing that we have to do now is we have to make a decision about whether we want a synchronization mechanism that looks that up in another thread, or whether we directly find the thread that we want to send that information to and then put the data in the pipe or down the channel. I think I'm going to go for sharing the sim worker information. Will I? Let's say that we now need to share the sim worker info objects. So we have a vector, vector of those that we create when we create a simulation. In Rust, you cannot just give access to that object. You cannot just give access to it like that. But you could potentially put that array into a reference counting cell. So a reference counter is the RC object. So what we want in Rust is that we cannot, so when we create a thread, we move into that thread the data that we want. So we cannot just put the variable in there. We cannot just put a pointer in the thread, because that violates Rust's borrow checking rules. And it has this fascinating thing that when we are now programming this, we have to think about these things that probably, at least for me, would escape me if I was programming in this type of language. If it didn't have the borrow checker, I would probably just pass that pointer in, and I would have some seg fault or a security issue down the road, right? So I get this sense that, yeah, Rust is really onto something here with this, because now we are forced to think about how we will share this memory in a safe way. What we can do is we can put the sim worker list behind a synchronous reference counter, an arc. So if we do that, we can then clone the arc to the vector of sim workers and then put that into the, can we? Yes, so we are now facing another interesting dilemma. What happens is that we have a loop, and we create the sim worker info, and then we create the sim worker. So it means that, so here's the thing, if we create gradually that vector of sim worker infos, we cannot put them into the arc. The reason we cannot put them into this asynchronous reference counter object is that we have to move the vector into the arc, but the arc is unmutable. That is also because it has to have that guarantee that we are now. It has to have a guarantee that we're not changing it when someone else is looking at it. So the question is, like, technically, what do we do? Perhaps we can still have the arc, but maybe we need to create the sim worker infos and the sim workers before we launch the sim workers. Can we do that? And then when we launch the sim workers, we will. No, this gets convoluted. So it is absolutely possible to do it this way, that we create the sim worker information first and then launch it, but it seems a bit messy. On the other hand, our alternative is that we keep all information about the sim workers in the simulation thread, or we create a new thread whose responsibility it is to distribute this infection data to the other workers. That is also messy, because then you get one more object that you have to synchronize. So that also has to have an element of control. That is not beneficial either. Okay, so I think our best way of sharing this information between the threads is to create a sim worker array before we start the threads, and then somehow move clones of this arc into those threads, so that they all have access to the sim worker array in an unmutable shape. But we will not mutate that array afterwards. We have to have access to the channels and be able to put data into the channels. So the only thing we need to check is that sending data down a channel does not require that channel to be mutable. So we will go to a point here where we will find, where we will see the threads send a signal that they are finished down the ready receiver. That this is a channel as well. We send that to the simulation. So what we need to check is if these channels and the send function requires immutable, and it doesn't. It requires only an immutable self and the data. Yeah. That means that yes, we can put all information about the thread into an arc and share clones of that across the threads. We should do that. I think that is the answer. So in order for this function, so again, what we're trying to do here is when we try to infect someone, we need to look up what thread to pass that information to, and then we need to have an index of the threads. So now we need to find a way to send that vector to all the threads. Okay, so let's do that. The way we spawn these threads is that we create worker infos, and we create our threads, our sim workers. What we need to do now is, I think, because we now need to pass the complete list of sim worker info to the sim workers as they start, we need to push this. We need to take this part of the iteration out and start that after we have generated all the threads. And then we need to pass into this spawn method here, we need to pass clone of the complete list of worker infos. That also means that the worker infos have to be inside an arc. And the worker infos is a property of the simulation. So instead of a vector of sim worker info, we will now change this, and we will put that inside an arc. So again, arc is a synchronous reference counter. We will import that. Now, of course, our code will not compile. What we need to do now is we need to, instead of directly pushing here, because now sim here, this is an arc now, the worker info. So instead of doing that, we need to take this out. And when we are done with this, we need to set that one. So we will do so here's what we're going to do. We're going to collect the array first. So we're going to create a let worker infos equals, that's going to be a vector. And again, here's that beautiful type hint, right? You see it doesn't know what it is now, but the moment we push some worker info into it, then it knows what that is. So we're going to create a mutable array of worker infos. Yeah, so now we are, instead of pushing it into the simulations worker info object, we are now just collecting our worker infos. And we'll take this part here, we're going to reactivate that in a moment. So now we are creating the workers, and we are creating the worker info. And now, of course, now we also need to keep a list of the workers. So we'll do mut worker. Workers. And that is also a vector. And then for each worker, we will take workers.push worker. And now this becomes a vector of simulation workers. So now we are creating workers and store info about them like this. The point of the sim worker info is again to keep the channels for the appropriate workers. Okay, so now what we're trying to do now is we need to make sure that this worker info, once it's full, it gets passed into the threads. Okay, so of course, right now, this would do nothing because it's not spawning the workers. So let's continue. We will take... Okay, so we'll now create the arc that we have in the simulations. The worker info is now an arc of vector of sim worker info. So we will set this one to a new arc, and then we'll move the worker infos into that arc. So what we did now is that we're basically, this variable will go out of scope because we are moving it, so this can no longer be used. We moved it into the arc, and now we can pass this arc into the threads by cloning it. Every time we clone it, the reference counter ticks up one variable, it ticks up one, and then every time one of the clones go out of scope, it ticks down one, and when the counter reaches 0, the data inside the arc drops. It drops out of memory, and this is how. So now we are deferring the memory management and this, the deletion guarantee for this data, the worker infos array. We're deferring that to runtime. So it's no longer the borrow checker that will, or no longer the compiler that will insert a drop statement for the data itself, but it will create, so now you can create an arbitrary number of immutable references to this arc by cloning it and passing those into channels. And it does so in a asynchronous way, but is thread safe, the way it is constructed currently. Okay, so let's continue. We now need to pass clones of this into our sim workers, and we need to start the sim workers. So we have this piece of code that we copied that starts the threads. Now we do a second loop, we'll start the threads. I'm not sure we can we loop through it like this? I have a feeling this is going to give us trouble, but we can try it. No, maybe not. What we're doing now when we're doing this is that because we are Because we are moving the workers into the thread, then we are taking them out of this iterator, right? Cannot borrow immutable local variable worker as, yeah. I wonder if we can just do this. Actually, maybe we could just do that. So for each worker we want to spawn, we now have to pass them the worker infos. And that means that in the init function here, we'll pass that. But we cannot pass sim.workerinfos into the thread, because then we take it out of the sim. So we're going to create a worker info. And that is the sim.workerinfos.clone. Not from slice, just clone. Notice how this now also became an arc, right? So we are cloning it, but we are not cloning the data inside. We're cloning the arc that points to the data. So we will now take this and we'll move it into the init function of the worker, and then we in this function we will now set this worker info. Worker. Yeah, that should be correct. So we'll go into init. Right now this one is not doing anything. So let's give it a task. You had one job in it. Actually, it will do more. It will allocate people as well. So it will allocate that huge array of people that we want. And we'll have a look in a moment on how we'll deal with the indexing, because right now each person has an ID that is its index in the array. But the problem is, of course, now we have split the array over multiple threads, and each of them start at 0. Okay, so in init here, we will now take self. We have to create, actually on sim worker, we have to now put the method. Let's just see if we can do this with the tooling. So we're now going to do self.workerinfos equals, and then we're going to say that we can take an arc to a vector of worker info, sim worker info, and that will be the worker infos, and then we do worker infos like this. Now we're moving that into this one. I'm curious now if we have autocomplete for this. No, we don't. So that means that we need to take this and we need to go up to the object, the sim workers, sim worker info here, and then we need to put worker infos like this. Okay, so what have we done? We are now distributing the list of the workers to each worker before we start them through the init function of that worker. So now in principle we have shared an immutable copy or an immutable copy, but we have shared an immutable reference of the worker info to all the threads. And the worker infos contain the channel that we need to put data into to communicate between the workers about what person in their array they should infect next. Okay. So of course this doesn't work right now. This is the initializer because we okay, that should work fine. And there we are. So the next thing that we probably need to do now is so in the simulation, we have now changed the data format of this worker infos. Yep. So this probably, so this requires us to wrap this in an arc. So when we are looping through, our, okay, so let's go down here. So we created this. So this should work now. At least until we compile it. It works in our head, but maybe not in reality. The question is if we need to change something in the simulations execution code now, because every time we call next day, we loop through the worker infos. So the question is, since we put this now inside of an arc, does it still work? And the same down here. the same in the finish. So in these three locations, we are accessing the worker infos. Is there a function here to look at where they are used? Find usages. Yeah, so we have 6 usages of the worker infos object or the field of this struct. So the question now becomes whether it compiles. So previously, sometimes I've been surprised that when you put something inside something like arc or rvlock, then you can just use the methods. So it's like it adds a layer to whatever struct it is, but it just continues working like before. Let's build. Almost 100% sure this is not going to compile. We probably made at least one mistake. Let's see. Yeah, here we go. Okay, so this is not pertaining to the first to the changes we did. So we appear to be having so infect day. Yeah. So basically, what is happening here is that in our sick days array, we have changed. Because a day infected should also be a U32. It doesn't make sense to be able to have negative days. So that's true. Okay. Mismatch types. Yeah, so here we are again. Same problem. Ooh, lots of trouble looking up here. Oh, this looks like a bad error. Let's see if we can get this one to solved. Okay, so this cannot be shared between channels safe. Okay. Interesting. Okay. So it seems like we cannot share, but we are already sending. Okay, so we cannot share the sender object between threads safe. We cannot have the same sender inside this this worker info array. We cannot have that there. That is of course a big bummer because we cannot. Okay, so what we're doing now is in the worker infos we do have the sender channel, but the send channel appears. You can clone senders. That we know because we can give sender channels. Okay, so when you create a channel, you get two ends. You get a receiver end and a sender end. The sender end you can share. The question is, but in order to share it, you have to clone it, and we're not cloning it now. And since we're putting this inside an arc, I guess somehow the compiler is figuring out that we are doing that. And then we cannot do that. So we cannot, yeah. So our problem here is the channel. The question is if we can clone all these, if we can sort of make a copy type or clone type, but I don't think we can because we have a receiver channel as well, don't we, in SimWorker? Yeah. No, in SimWorker info. So somehow actually we have. Am I doing something wrong here? Remove this one, right? Because we're not supposed to have. It's the SimWorker that we want to have that on. It's just to make sure that we're not screwing this up because of something stupid. We need to make sure what happens when the SimWorker is initialized and that it gets that and then says that. Yeah, so that is correct, but it still probably doesn't compile. Sim. Yeah, we were actually surprised it let us do this without complaining before our compilation. Yeah. Our problem remains the same. We don't have a, so we cannot share this easily between threads. What is the sim worker info? Let's have a look at that field again, because there might be solutions to this. Yeah. The sim worker info contains information, of course, about each worker, and it contains information about what index its people lie in. So what we'll do when we want to infect, say, person number 5000, is that we'll find the sim info worker with that person ID in range, and then in the infect sender field we'll send the info. The thing is that we should be able to clone this, because all these values can be cloned. We know that we can clone sender channels because it's a multiple producers, single receiver type channel. So we can clone them, and I'm wondering if we just pop this derived trait here with copy clone on top of that. Are we allowed to do that, or do we need to implement a function to clone this sim worker? Because if we can clone the sim worker, then we can clone the entire array of sim workers, right? No, we could not. The field does not implement copy. There's just clone that we are implementing. We were allowed to do that. So what I wonder now is if we can instead of passing the arc in, can we just clone the whole thing? Is that what we are doing here? Let's now take the we can just try this, and if it doesn't work, we'll figure out another way to do it. Let's remove this dead code. So in the sim worker, we will now actually get rid of these arcs. Instead, now we pass a copy of this vector, or a clone of this vector, because now we have the clone trait on sim worker info. So I think that clones all the fields. So now also in the worker infos area here in simulation, we will because now we want to make this a copy type basically, or clone type. Right now we're removing the arc, so that means that we have to go back down here again and remove the arc like this. So all these fields that we are now implementing, we are now just implementing them as vectors inside of vectors inside of an arc. And the init will now, instead of taking the arc, it will just take a vector. Like that. So when we are now creating our workers here, we will, yeah, so this is actually now just a vector. So the question is, are we now allowed to clone it? Okay, so we do mismatch type. Let's see where that was. That's fine, it was the same problem. Okay, workers does not live long enough. Now we're talking. So I wonder if we can Okay, let's see here. So what are we doing? What are we doing wrong? Let's see. Okay, so we now have a workers array. And for each worker, we are moving the worker out of the vector into the thread, which gets spawned. And we are completely apparently allowed. It's not complaining when we are cloning this sim worker info array. So that probably means that we are cloning out the channels correctly. But it is complaining here that this worker is not lived long enough. So I'm curious why that is. What I wonder about is if we are somehow messing up this array here by putting. I wonder if we can we can consume this array instead of iterating over it. Because we are changing it here. But I wonder if we can just grab, if we can take all the workers out instead of iterating over it. Then we're not dependent on an iterator. We're using a sort of destructive destructively working over it. Are we allowed to do as hr mute like this? Can we do that? Are we allowed to do that? Question of the day. No, so it is the same problem. We don't actually want to borrow the sim worker here. Okay, now we get this. We get the same kind of problem here. Cannot be shared between threads. I am a bit concerned about this. What we can try and do is we can try and consume this array instead. So we'll say let mutable spawned. Okay, let mutable done equals false. And then we'll while not done, we will take one worker out of like this. So what we're going to do is we're going to take workers, and then we're going to remove the first element. Let worker equals like this, and then we'll say we'll match worker to see if it is if it was a valid worker. That's not what we wanted to do. Okay, so this should give us an option, right? It should not give us this. So we don't want this to panic. So I think we can do a try remove, can we? What does remove item do? Unstable, recently added. Okay, so let's do it a bit differently. While workers.lang bigger than 0. We take worker and then we take workers remove 0. That gives us a sim worker. I thought it would give us an option, so I'm a bit surprised that remove didn't allow us to, or didn't give us an option so we could just match whether there was something else, something left or not. Okay, so now we are, and this will be a mutable worker. Then we clone it, and we're probably gonna get the same. Okay, share cannot move out of self people, which is behind this mutable. Okay, let's see. Okay, this is a problem in a different place, and it is the last problem we have. So it seems okay. So actually, I think what we did up here to create when we spawned the threads did work now. We are consuming this array and we are spawning the workers as we are going through, and it no longer complains about that. We are cloning the workers info array instead of sharing it. And the reason we can do that is it's a small piece of data. We can allow ourselves to clone it, and B, we can clone the senders. So that should work. Okay, so now we have another problem here in next day. So it will not allow us to, yes, we were looking at for each person in self people, we were looping through the array, and we were not allowed to do that. Cannot move out of self people, which is behind the mutable reference. Okay, so this is a good point. We don't want to move person out, so I think we can just do this, and then we'll borrow that person, and it compiles. What happened here is that the iterator apparently tries to move the person out of the array. Wasn't that exactly what we were doing just a moment ago, though? But I guess, does it mean that the iterator moves the person out and then doesn't put it back? Or just puts it back at the end? I actually don't know exactly how that works there. Almost calls for a small test. But I think if you iterate over, it shouldn't be destructive to iterate over collection. Certainly can be if you want it to, right? We do want it to be destructive to the collection. We want to consume the collection and do something for each item in the previous part of the code. But right now we don't want that. We don't want that to happen here. Okay, anyway, we seem to be compiling, so we can run it too. At least it exited with code 0. What I think we can do is we can add a little bit of debug information here. We can add an output that says that tells us the day we are simulating. So we can do print line day, then we do day, and then at the very end we're done. Like that. Let's do it. Yeah, so it does loop through, and again, we proved in the last stream that this synchronization method that we are using does work. So we know that it does indeed ask all the threads to execute. Just to make sure, we can ask the threads to print something on. Actually, what we can do is we can in the threads. Let's put a breakpoint here. Actually, the self person array is empty at present, but you can do a print line here that said process day. What I'm curious about is if all this memory is correct, right? Well, Rust should guarantee us that, right? Okay, so we have successfully stopped it inside one of the threads, and indeed we have several threads, 7 threads. I guess it's the main thread plus 6. And we can have a look at self and see what we have. So self currently contains an empty people vector. We will create that next, and we'll deal with the sort of the logic of the simulation. We spent a lot of time getting this synchronization to work, so we've sort of lost track of the logic of the simulation we're trying to do, right? We have a worker inference array, and indeed that contains sender channels that we cloned. I'm going to assume that they get cleaned up as they get dropped out, and that these have some kind of reference counting so that they will work, or that they have some internal mechanism that allows them to be cloned like this. Maybe they have an RV lock inside, a mutex inside that makes this function. Because if these created a memory leak, it would not be very nice, and it would be counter to the point of what Rust does for us, right? So we do have the channels. They are now in memory. We have total number of people, and all that is good. Okay, so principally our simulation now does appear to work, right? We should now perform the actual simulation. Okay, so I'm going to take just 1 second to less than 2 minutes. I'll take 2 minutes just to grab myself a glass of water, and then we will get into the actual coding of the simulation and try to get it running again. So our goal is now to be able to infect people and get the output, and then it will be really interesting to see if we have any kind of performance benefit from this pivot into multi-threading, or if keeping it single-threaded would not be so bad, considering that very little work happens in each individual thread. Okay, most of it's actually just pushing memory around. Okay, so I'll be back in a moment. I just need to get myself something to drink. So 2 minutes, like that, in case somebody drops in. Okay, that did not work the way intended. There you go, and then I'll be right back. Okay, everyone, we are back. If anyone watching has any questions, feel free to ask in the chat, of course. I'm also especially curious to hear how other people are using Rust. And if you're watching this on demand later on YouTube, then please let me know in the comments and I will see if I can reply to them too. I upload all these videos to YouTube after they are done to provide sort of a record of this little adventure that we have going on here. Okay, so let's continue our coding. So again, we have now got our threads running. We have successfully distributed information and communication channels to all the threads for all the threads. So all the threads now know or are aware of the other threads. And we want this because we want the threads to directly send information about new infections to the threads that are responsible for the people that will be infected. So the thing that we will start by doing is we will create the people array with the individuals that are infected. And then we will distribute that on the, actually we will calculate how many people should be in each thread's person array, people array, and then we will have the threads create those arrays on initialization. And this should amount to the total number of people in the simulation in total. It means that the last thread might not get the full amount of people. We have to keep that in mind. Then in the SimWorker information, we need to, in the SimWorker info objects that are now distributed to all the threads, we need to have the range of person IDs that are in each thread, so that when a new infection arises in one of the threads, you can look up in the SimWorker infos what thread should receive the notification that that individual should be infected. Okay, so we'll do that. So, okay, so again, it compiles, it runs. We can run up to 300 days. Actually, let's get rid of that. Let's get rid of that little notification because that is super annoying. Or actually, let's keep that in. And the reason is that it's nice to know. It's nice to know that it's running. But if we just give it a little Does this look reasonable, or does that just become crazy? That does just become crazy. So how is this? If you want to print with the modes, we can say if day mode 10 equals 0, is that it? And then we can print line. We can actually print just an empty line. Simplify macro for that. Not look very good, does it? Why does it become like that? I guess, or is it? No, it's percent like that. Okay, that's right. Okay, there we go. So that looks a little bit nicer. It sort of gradually pops these out. If they took a little bit of time, I guess they would sort of pop in like that. Yeah. Okay, so that's one way we can output our information and have some overview, at least to know that it is ticking, and get some idea of the rate at which it's going just by looking at the console output. Okay, so let's look into how many people we should create in each thread. So what we need to do is we need to go into simulation, and we need to inform each thread about the range that it will work on. So when we create the worker, we do have a actually with worker info as well, we have a range element argument that contains to and from. That is the idea. So we now have n threads, which is the number of threads. So what we can do with that is we can of course calculate number of people in each thread. So we can do number of people in each thread. Or each worker is a better. So we have the n people in our simulation, so we know that we can just should principally then just take let that was n worker people equals, and then we say that is the total number of people, so it's n people divided by the number of threads. Let's say that we now have 100 people, and we divide it by 10 threads, we will be on 10. So we will now have a number of people. There will be some precision in this, but precision problem here, but you can just see how this works. So in this case, we can actually just get our calculator going. So we have, we're going to simulate this initially with 100,000 people, and we're going to do it on 6 threads. So yeah, of course, we get not a very round number. I guess it will round it to, I wonder when it does it like this, does it round it up? Since there's not floating points here. We can just try this and see how many people it actually ends up simulating. This is the number of people that go in each thread. So we will create for ourselves, we will create, yeah, so the first index of that individual, so the index that the threads start on will be the iterator times that, because each contains that number of people. So this one creates a communication channel, so channels. So let's find the range, or calculate range. Let thread start or start equals I times n number of people, and let end equals I times n is actually start plus the number of people. We have to add 1 here. Subtract 1. Guess we'll find that out. This is now going to be the start to end range. There's range start and range end. Yeah, so let's say that it was, so this, if it was 10 people per thread, it would be 10, 20, 30. Yeah, so it will be, I think I have to subtract 1 from this number. Actually, I can just do that. The order is irrelevant here. Like that. And I hope this would work. Now we know the range of that worker. In the sim info, we will copy this one in, the range start and range end. usize. Maybe we can just do as usize to cast that. The usize is the type that's used to indicate positions in arrays and vectors in Rust. I guess it means unsigned size, and size is probably like 64 or 32 bits. Okay, so now we have told the worker info where we are. We do want the worker to know. So we will actually give it the same. We'll give it the same property. That means we have to go into SimWorker and provide it with the range, and that is the same as the SimWorker info. Actually, what this is ID range. Maybe that is personal. This is actually an ID of the SimWorker, so it's not the same. Maybe that is a bit confusing. Let's put that back to range. Of course, now I also have to edit it here again, since I was using the Autocomplete for that, or the tooling for that. Okay, so now both the worker info and the SimWorker knows the range. Actually, we can make this even prettier. We can say range equals, and then we can create that tuple, which is range start as usize and range end as usize, like that. Of course, you could put this inside here. Sometimes I like to make it a little bit more verbose. Then I think in Rust you can now just do this, and it takes that variable and copies that in. This should be a copy type, so we can do this without moving it. Okay, let's see if it compiles. Nope, it does not. Expected value found built-in attribute start. Okay, so I guess start is not a good name. Yep, there we go. Range start is what we're going for. There you go. So that compiles. So now did we leave our breakpoint? We didn't. But right now each worker is aware of the. You can check now if this actually became the if it does what we expect. Can we break here? Can we break? The debugging here is not always. Yeah, there we go. It's not always optimal. So let's have a look at this worker infos and see if the ranges are correct. So the first one has from 0 to 16665. The second one should then have, yeah, so that's correct. From 166 to 3221, yeah, correct. So the last thing we need to make sure is that the last one is not longer than the total number of people. But that should not be a problem, should it? Let's have a look at that. Or will it be a problem? What we need to make sure of is that if it's the last range. Okay, so if if I equals number of threads. So for the last one, we want the range end to be the total number of people. So we just need to make sure that that is the case. Okay. Now we've done that. So we're now going to have each thread on init initialize the people array. The sim workers have this initialization function, which takes the sim worker info clone that we looked at earlier. But now we're also going to use it to initialize people. So we're going to assign each person an ID. This is mainly for debugging purposes. We're going to assign each person an ID corresponding to to what we or to the actual ID of that individual, because I think that will help us in case we get into trouble. But we're gonna now create. We're gonna say that self people equals a new vec of person. Actually, we can. I think we can just do vec, and we're gonna assign it with the capacity that is similar to self.range 1 minus self.range .0. The reason we want to do this is that we want to initialize this so that we don't have to reinitialize the vector every time we push a new person onto the vector. Then we're gonna loop through the range. So we're gonna do for ID in self range 0 dot self dot range dot 1. So this is a tuple. This is the way we say we want the first and the second value out of the tuple. Okay, so now we're going to create the person. So we're going to say, actually right now we can just push in self people dot push. We're going to create a person. And let's see what add missing fields. Clinical course is currently an empty vector, and the day infected is none. So now we are just simply pushing people onto the array. Let's run it. Yep, let's put the debugger again, and we are on the next day, so it should be implemented. Let's try and see. Yep, so now we have our 16,000 or whatever it was people in each chunk, and we find that they are not infected and that their clinical course is empty. Does this actually mean that I can stop it, and by switching here, can I stop it on the same thread in multiple? No, I think we just stopped it. Or can we? Can I switch the thread that we stopped it in? So now I'm going to go to the last thread. Yeah, ID 5. That's correct, because this goes from 0 to 6 people. And let's have a look at their IDs. Oh, the people don't actually have IDs. I think we want that. Or is it unnecessary? Maybe it's unnecessary. Let's not give people ID. We will just go for their index. So because we are now choosing, we're finding the person that an ID corresponds to in another thread. We need to say that the index of the person will be the range which we start. It will be the index minus the start range, and that's person's index in the people array. So let's continue this. Okay, so the next thing that we have to do is now we are looping through the individuals, right? When we do run and when we do handle next day, so let's see, handle next day, we are indeed looping through the individuals, and we're looking for infected individuals. The next thing we are going to do is we need a way to so let's see here. Okay, so okay, so now we are in the next day step. We're now looping through the people, and we are finding the ones that are infected. If the person infects another one, then we need to find that person and send information to the correct thread. So we will call, if that person infects someone, we will call self.infect and then provide the ID of the individual that gets infected. That function is down here. What this function has to do is it has to look up the ID, or it has to look up the thread that carries that individual. So I think here we can use the iterator, can't we? We can say, so now we have this worker info sting, so we'll find the correct worker info. So let's first just run, see everything compiles. No. Ah, interesting. So now we have one of these borrow problems again. So what we are doing here is, of course, we are not What happened here? Let's run this again. Now it compiles, but when we say self-infect, cannot borrow self as mutable because it's also borrowed as immutable. Yeah, so we are now looping through self. We are borrowing self to the iterator. And then we're borrowing ourselves as immutable. So the question is, if for this to work, if we need to borrow ourselves as mutable. Yeah, so we cannot borrow ourselves as mutable more than once at a time. So the problem we have now. Okay, so yeah, okay. This is of course also interesting, right? So we're looping through this, and because we're doing it in the iterator here, we are borrowing ourselves into the iterator. That must be what is happening, right? And then because we are inside the iterator, we have at this point we borrowed ourselves as immutable, but here we are borrowing ourselves as mutable here. So we have the same. So we have a problem again that we are that we cannot borrow ourselves as mutable more than once. We had this problem before. And what was the solution here? Or is the problem that we're borrowing ourselves into this match thing? I wonder if I'm just going to try this because this is very curious to me. What happens if I put if I just infect number 1 all the time? Because now we're doing it inside the iterator rather than, yeah, it's not, so that doesn't work. So it's the same problem. I think one solution here is that we don't have to. Yeah, so we had exactly this problem before. Okay, so an immutable borrow occurs here, borrowed later here. And a mutable borrow occurs here. So we found a good solution to this, didn't we? But it was not this does not really work because now we're moving self in there. I think that would work. Actually, we might get around this by saying that we don't actually need to do anything here. So we might be able to get around this by removing the fact that infection does not have to be we don't have to be self-mutable here. So that could be one solution. The other solution would, I think, actually is not to use the iterator here. I think we can. Yeah, this is a little bit clunky because one thing we could potentially do is we could do a for loop here with the length of self people. But I think we end up in the same problem. We can try it for I in 0 to self.people.length. So what we're doing here is we're borrowing it right there, but then we're not borrowing it again. But now we need the person, so we say let person equals self people.get, and then we need the person to be, in this case, is the person mutable here? No, the person is not, so we can just do get I dot and then unwrap. It did not like that. Yeah, oh yeah, of course, it's because it's missing a clause here. So that works. Okay, so apparently the reason here is that when we are doing this, we are borrowing self to get length here, but then and then we're doing it again here, but then we are borrowing out this person reference, but we're apparently not borrowing self into the iterator. That must be what is happening here. Okay, let's keep going. Okay, so that works. Now we don't actually have, I think, to put mutable here. The reason I did this was just to check if that worked, and it did work. So in that sense, it's cleaner if you just use the iterator like this. I think. Let's keep it commented there in case we need to. In case we need to go back. Okay, let's continue. Now we are in the Infect, and what we need to do is we need to find the worker info that has the ID of the one we want. So let's go for so that has this ID in its range. So we will now do, actually I think we can just do self.workerinfos, and then we can filter these. So we can ask for an iterator. We'll filter, and the filtering function will take the worker info, and it will simply return, it will say vi.range.0 is smaller than ID, and then worker info.range.1 is, no, it's the opposite. So no, it's the, no, so it, and that range is bigger than ID. So let's just check this. Maybe this sort of syntax, maybe it gets a bit messy. I usually like this syntax, but because of the iter and sometimes the unwrap and these sort of hints, it gets a bit messy. Let's just check that we're doing the right thing. We're not, yeah, so we're getting some error message here. Okay, so we are looping through, we're iterating over worker infos, and then we're filtering, and the filter goes for worker info range. Okay, so if the worker info range, the first one is smaller than ID, and the last one is bigger than ID, then we know that we have it, but we are getting an error here. Why is that? Not sure I understand why we're getting that. It should be fine. Expected one, yeah, so that's good. What am I forgetting? No. Yeah, so we're closing that. Now we go here. Maybe it's better to put a semicolon. No, I don't. What? Do this one more time. Self.workerinfos. Did I say first here? No. Here, filter. The filter takes the worker info or the worker. Then it has a clause. And it says worker.range.0. You can just try this, just to check it's in a simpler construction. But of course, I forgot the for loop. So it's for worker in. I forgot the for loop. What we're actually looking for is we're looking for the first one. What we want to make sure of, in a way, maybe this is not a good solution here, because we want to make sure that we panic if we didn't find it. Actually, we are gonna do it a little bit differently. So for each worker info and for each worker in worker info, we are going to borrow it. Then we do, so if w.range.0 is smaller than ID, and w.range.1 is less, no, it's bigger than ID, then we do it. What we want to do is we want to make sure that when we find it, we return. But if we didn't find it, we don't return. Then so if we didn't find it, we will panic here. We'll panic by ID not found. Person ID not found in any worker info. When we find the worker info, we will take the infection sender and we will send the ID to that one. Okay, so here we are now creating a cyclic horrible structure because we are actually calling self-infect in this one too. So we will work with this one later to see what actually happens when the infection occurs. But the infect function we now retooled to infect someone in the correct worker. So this let's hope it compiles. It does compile. Does it run? Compiles and it runs. Okay, so we are now infecting someone regardless of what worker they are in. So we have hopefully achieved that parallelism that we wanted there. And that is presumably a good thing. Presumably that's a key element in what we are doing. Okay, so anything that goes in this pipe comes out here in handle infections. So we need to deal with handle infections up here to actually have the individual get infected. So we are going to go here and we're going to take the infect. We had actually quite a large thing here that stated that a large chunk of code here that created the infection in that person. So we will move it here and we will say create infection. Create infection. So, okay, that's not good. That's not actually what we want. Yeah, okay, all right, okay, I see. Okay, so what create infection does is it takes the ID of an individual and the current day. Oh, there's a challenge. No, because we are already, because handle infections need to be told what day it is, because we are we're telling the person that, or shall we revert back to the idea that we had before where we simplified the way person was, because right now we made it like day dependent. That became a bit messy. It is prettier if we're modifying the person each day. I like that, although then the numbers we are getting out of this gets less comparable with the most recent version of the simulation. When we changed the logic of how the infection progression worked in the previous streams, we did find though that the effect on the time it took to execute was minimal. So I assume that this means that we can take this, we can revert back to the mechanism that we had before. Okay, so what we will do now is we will create a person to find. We create a function to find the person by ID. And what we'll do is we'll take a mutable version of self. No, we will not. We'll just take self. I think we can do that. Can we do that? Find person will return a mutable reference to person. Yes, I believe so. I hope so. And it takes, I think maybe self has to be mutable. Let's see. And it takes the ID of the individual. So what we know is that the ID is the actual ID. So we'll do let vec ID, the vector ID, which is the index. Actually, it's not the ID. It's the IDX. The vector index is the range of us. That's the ID that we get minus the starting range. And the reason for that is that if our individuals are from starts at 10 and we're asking for 15, then we want to do 15 minus 10 to get the correct vector index. So this way we should get the vector index. So what we will then do is we will return the self.people and we'll do get mutable vec idx. And that probably has to be mutable, cannot borrow immutable local variable self people as mutable. So indeed, in order to return this mutable person, then we have to be mutable ourselves, which makes perfect sense, right? This is probably how the mutable restrictions propagate through your functions in a minimal, simple way in Rust compilation. Even though there's probably nothing minimal about it, this static analysis here is probably really complicated internally. So now we are actually we will change. This is like idiomatic in Rust that you use at mut if you want them to be mutable. So we will do that. This is yeah, this cannot have a semicolon. Oh, trouble. Yeah, expected person. So yeah, of course, this is an error checking thing. We will skip the error checking. If you wanted to check and deal with the person not being here, we would return option itself, or we would just check the error here. Okay, get person mut is now there. So now we will, okay, so when we create infection, we will get the individual using this function. So we're going to document this. We're going to say get a person from its ID. Okay, does it compile? No, it doesn't compile. Mismatch type. It's probably because we are not using this correctly, or we're not doing this at the moment. Compile. Now we update our create infection function. So to get the person, we will take self.get person mutable and we'll pass in the ID. That returns as a mutable person. I'm just going to check to be sure that this actually works. It compiles just fine. Okay, so here's the thing. We want to look at the person's state. And in this slightly convoluted updated version that we created earlier, we don't mutate the person's states. We actually have a function that figures out the state based on the day. So we can make a decision if we want that to continue or not. And I think that I want to get rid of this. I think we will, it's much prettier if we can now just look at the person and ask, what's your state? We don't need to get this status on day. Although it does, it has simplified things in other parts of the code. Okay, for now, let's just keep that in. Let's just keep that in for now, yeah. Okay, so day here's an I32. We don't want that. We want that to be an unsigned 32. I think we changed that somewhere else. So we did have a problem with this function previously in one of the other streams. So what happens here is that a person, if you borrowed them mutably here, it became like a shared reference problem. So I'm not sure this one's going to compile, but we can try. We can see the logic first and see logically does this work. Okay, so we're taking the person and then we are matching the status on that person. And if the person is not susceptible, if the person is anything but susceptible, then the infection doesn't bite, right? Either the person is recovered or already infected, then we don't do anything when we try to infect that individual. So what's happening instead is that if the person is susceptible, nothing happens. If the person is any other state, then we return. Nothing happens, and this is why the curve flattens on the top. When you see the number of sick people, the infection gets less and less people, has less and less opportunity to attack new people. Okay, so if we get to this point down here, we have not returned, which means that the person was susceptible. And then we need to create our course, our clinical course. So we create our vector of sick days, which is 3 times repeating this pattern you see here, and it concludes in the person being recovered. And then in fact, we get the person again here. I'm gonna take this out for now, and then we'll see. See, there was some complexity with this because we had to pick a random ID here. But this one, we will actually change now because we can simplify this now significantly with the way it works. In fact, we need a new pick random function. There's really no point in this function being on the object itself. You just need to say that. There's really no point. And the reason for that is, of course, self now is not a simulation, it's a sim worker. But the reason is that before we had to use this because we had to get length of the people area. That's not the one we want to use anymore because now we have a field called total people. We know the size of the simulation. That is not dynamic, it's static, it's set in the beginning. That we don't add more people to the pool as we're going along. What's happening in this function right now is that it just takes the total number of people, and if this squeals, if this causes problems, we can easily make this a static function and just feed this n number of people into it. What this does is it just picks a random integer in this range. Probably there is already a function to do that, but we know that this works, so we will keep it going. Do we compile? Of course we don't compile. Non-item in item list. Well, that is a new one. Yeah. Okay. So we have a stray. We have a stray. Stray comment, multi-line comment, and the terminator there. Okay. Let's try it again. Yep, so I think we are here now in the same problem. Okay, so we are, so this is exactly, okay, so what happens here is that we are, to get this person here, we're borrowing ourselves into this function. As long as this person exists, it seems that this person is dependent on self existing. So when this person, so as long as this element is here, we cannot call pick random. But we can actually we can call twice. We can get the person back here. We can call this line one more time afterwards. First, we're going to try this. I don't think this compiles. Oh, it compiles. Yeah. Okay, so this is that kind of Rust brain teaser, right? This is fascinating stuff because we had that in scope. Rust says, you gotta clean this one out before you can do that. Before you can call anything more on self-mutable or immutable too, I guess, you gotta make sure that you handle this person object. And what happens here is that the person drops out of scope here, and then we pick up the person again afterwards. Now we have to call that function twice. That is not nice. So instead of doing that, we don't need to depend on self here. We can simplify this and we can say n people, which is a U32, right? And then we will say, because now we don't need self here anymore. And what we have now done is that we've created a static function. So we can say take sim worker, pick random index, and then we can say, yeah, we can, right? We can do self.n total people. And then we don't need to call this function twice. Cannot use n self total because it was mutably borrowed. Really? Cannot use, that surprises me greatly that we cannot just do that. Okay, we have the same problem, right? Okay, so when we do get person mutable, we do borrow mutable self, that's fine. But can't I, yeah, so principally what we can do is we can say n total people, and then we can do self. No, we cannot. Yeah, we can. We can do n total people. We can take that one out. Jeez, this is some messy stuff going on. We can take that out, and then instead of calling self here, we can do that. Because what we did now is we cloned that value up here, and then we're just using the clone there, and this should compile, and it compiles. Yeah, that is a bit of a, this is like a, what's it called, it's funny how these things sort of turn out, right? The question though is, while I'm sitting here, am I feeling that this is like a restriction or a limitation? Does it feel confining to have these things? No, I don't, because I know that it's there for my protection. In a way, I think I understand why these things come about, and probably as you get better at Rust, you will figure this more out. I didn't feel now like this was a problem that I had to do this. It's more like, okay, I accept that Rust needs me to do this in order for this operation to be safe. And the benefits are, you know, speed, no garbage collection, minimal executable size, and like compiling to any platform regardless of infrastructure on that platform to support Rust. So it's nice, it's neat. Feels like I can trust it because of these things, so it's good, it runs. Now we have created our infect function, and that is really important. Okay, so the thing that we are going to do next, now we can create an infection. It is working, it should be, okay, so when you handle infections, we should now be able to create an infection in that person. When we handle infections, we know that it applies to our list of people. So we should now do self.create infection. And it takes the ID of the individual, this ID, and it takes the day. So what has to happen is that we have to, when we do handle infections, we do now need to pass the day information into this function. And handle infections is called from see here, it's called from the run loop. So we need now to put the handle infections, we need to give it a day. And then it doesn't do that yet because there's no data associated with handle infections like this. And then we need to go into sim, and when it loops, when the simulation does next day, we need to pass the day into handle infections. Now we're handling infections for that day. Takes one argument, none were supplied. Self-handle infections, yep, of course it's day. A lot of problems with that code there. Okay, there we go. Does it compile? It compiles. Does it run? Runs, and it doesn't segfault or crash or whatever. It doesn't crash and burn. So here we are. We are moving along. We need one more thing now, and that is we need to seed infections. So when we are starting out, we need, if there are no infected people in the population, then of course the infection doesn't start. So we need to kindle it. We need to give it we need to put a little bit of gas on the fire for it to start initially. So we have in our sim, these functions are getting horrifically long now. So yeah, this should definitely be tidied up. But I don't want to spend too much time on the stream to do that either. But we have a parameter here called nseed, which is a parameter that says how many people we seed with simulations. So I think we're gonna create a function for that, since we already have such a long initializer there. We're gonna do a function called seed, and it takes the number of seed, or does it? Do we store that? I don't think we do, but u32. Can throw away this variable when we're done with it, or we could store it in the sim object, like if we want to do logging or something. But yeah, what we are going to do is that we are going to borrow. We're going to randomly, or not really randomly, we're going to loop through our sim workers, and then we're going to distribute infections in them until we are done with this. So what we're going to do is we're going to say we don't actually need to keep this index. We just want to do this n number of times. We do from 0 to seed. Yeah, so it's in 0 to seed. And what we want to do along the way here is we want to find, actually, now let's do this a little bit differently. We're going to loop through the sim workers, and the first thing we want to do is ask them to handle the infection. We don't want them to start. We want them to start by handling infections, because that is the seeding round. So the seeding round is an initial step that we will take. Okay, so let's think about this for a second. We then need access to the workers. Yeah, so we do already on sim have worker infos, so probably it starts to make sense to have self here. So we're going to do for worker in self, or for worker info in self dot worker infos, and this can just be a borrow. I hope we're allowed to do that. Yeah, so for each worker info, I'm going to call it WI, I think. Then we're going to have a let's mutable seeded equals 0. Then we're going to do worker info dot inf sender. Is now we actually need to, oh yeah, of course we have to what we have to do is we have to we would like to create, yeah, so now this, okay, so we have the same problem as with the worker infos, that we need to know what worker info has this and this variable, right? Or has this and this ID. So now we need to pick an ID in this worker, and we want that to be random. Because the numbers are so large, we're almost guaranteed that we will not pick the same person twice with the random. So I think we'll just do that. From that worker info, we will just pick one ID within that worker info's range. But because this is like this kind of loop again, I need to see if this compiles and if we're allowed to do something with it. Yeah, are we allowed to, for instance, if I now send inf sender.send, can I send the number 1 down this pipe? Am I allowed to do that? Yeah, I am. Although this would certainly crash, or this would panic the threads. We can try that. Does it panic it? Oh, it didn't panic it. Yeah, because it doesn't have a seeding round. Is that why? Okay, that is a bit intriguing. Because why would it not crash this? Oh, we're not actually, because we're not calling the function. That's why. That's not ridiculous at all, is it? Okay, so seeded will also be plus equals 1 for each round. And if seeded is bigger than unseed, then we will break. Okay, so now let's see if we can call it here. We will yes, actually I don't think we need to have a seeding round. We can just do this, and then we can wait for, what will happen is that on the first day, on day 0, no one will be infected. Yeah, that's not good, right? So I think we're going to skip adding a separate seeding round now, because our mechanism is simple. But the seeding round would be more correct, so probably we would have to add that later anyway. But let's avoid that for now, because we want this to just work. So we're going to do self dot no, actually it's not, yeah, right, it's sim, because it doesn't have self. Sim dot seed, then seed. This should now crash them. Yeah, and it does crash them. It should crash them because many of these don't have that number, right? So we added a panic. So I really hope that's what's happening. So instead we want to pick instead of passing 1 down the infection channel here, we want actually let's just double check that it crashes on the right place, right? Is this the point where it panics? It should definitely not panic on this line. It should panic here on 293. There's no point where I can see that. There's a multiple of them should panic. Attempting to subtract with overflow. Yeah, makes sense. Actually, what's happening here is that the ID is we have an unsigned integer, right? Integer, and then we're trying to subtract a number from it that it cannot subtract. So that makes perfect sense. So instead, we now want to, in our seeding round, we want to pick a number that's actually within the range. That's what we want to do. So we'll figure out this number. So we'll have an IDX, and then we will calculate the IDX based on the worker info. So the worker info range, let range equals worker info dot range dot 1 minus worker info range dot 0. So if it went from 10 to 20, this will now be the range of 10. So we want to pick a random number in that. So we're going to do let IDX equals range times random. This should not create a floating point, right? Let's just go there and see if it compiles, of course. Stop and rerun. Yeah, good. Cannot satisfy. Where's our problem? Cannot satisfy U size as U size. We can actually change range to as U through 2. Nope. What if we just did this? I think I had to specify to IDX what it is. No? Because if I go there. Yeah, because I'm passing that into. Ah, I see. Funny. So it does, random does actually pick a random number. It's not like in most languages where it picks. If you ask random, it asks you, it always gives you a number between 0 and 1. It chooses the right thing. So what we want is, of course, we do want this to be float, don't we? So if we did F32 here, I just want to see now what that number is. Type annotation is needed. Yeah, so we ask for F32, a floating point. Now we are getting the right thing, and then we want that within the range. So we multiply that by range. Does it remain an F32 at that point? Type annotations needed. So this is we can convert that to an F32 as well. Cannot infer type for parameter t. Do we have to do this maybe? Okay, let rand equals rnd equals random. This is an F32. And then, yeah, let's just do that. We know that's going to work, and we know that we're going to get a small value. And then we want the index to be the random number, RND, multiplied by, okay, we couldn't do just range, I think. Add save cost to F32, yeah. Okay, so now we have, okay, so the IDX is now this, yeah, and then we need to round this, round as U32. We're not allowed to do that, so let's do round at least. Yeah, it's because we have this. As U32. Okay, so now we are picking an index. We'll need it one more time to see if we get the same number, and we didn't. Good. Yeah, that's good. So the IDX should now be correct, and we can infect randomly that index. But in order to do that, let's usize. We have to add the worker info range to that, because now we are we're seeding these infections within the range of the worker we are looking at. Fingers crossed. It runs. Now the question is how many infected people and so on do we have? Have we actually successfully, on day 300, how many people are infected in our simulation? So yeah, it's becoming a little bit complicated now. Okay, so we don't have a way right now to report how many people are sick and so on in the various threads. We have seeded the infections, so in principle it should now do the same thing as it did before. Boy, did this become convoluted compared to what it was when it was single-threaded. Because of the need to synchronize all this data, everything got really complex in contrast to what it was before. So the question now is, how do we report the number of sick and so on each individual day? So there are several ways we can do that. We can have each thread independently record that information. And then we can sum it up at the end once the simulation is done. And I actually don't think this is necessarily a very bad idea, because it means that the threads don't have to communicate anything until they are done. On the other hand, then they do have to keep that information until they're finished. But if we want simulation to collect this information along the way, then we need to pass some data back to simulation along the way, and because that requires us to have some channel data. So we could use the ready channel for that, right? But that adds some complexity as well. So I have a feeling that the nicest way for us to do this is to collect that data at the very end. And another thing we can do is for now we can count it up as the simulation is running, just to see that it works. And then one more thing we can do is that we can actually start timing it now to see if we are actually getting some kind of speed increase now. If the only thing we don't do is collect the information at the very end, but we can collect it along the way. Ooh, it's becoming big, isn't it? Now it's like, what was it before? It was like 100 something lines. Now we're up to at least 350 lines, counting main. So it's becoming big. So you gotta, if this is the optimal way of organizing this multitasking, then you gotta be ready for that, to your code to get bloated or significantly more bloated. The amount of synchronization code in here is pretty large compared to the code that actually performs the simulation. Okay, so what we will do here now is we had this update stats, yeah. So we can uncomment this now. We had this function already that counted up for each thread the number, or for the simulation it counted the sick people and so on. This should hopefully just be I wonder if this is effectively just a drop-in thing. We can just, instead of using this on sim, we can now use it on each individual thread. And does this compile? No. Types. So day is U32. So that's the thing we updated. A field output. So we are we can skip this output and just do the count. This function operates. So we're now going to print the line, and then we're gonna report the ID of the thread. We're going to do thread ID, and then we'll do self.id. Then we'll report sys, inf, and rec, which is the number of people that have these states in our infection at present. So we will do, that's 1, 2, 3 fields that we want to put in this print line, and let's go. So we now want to call this update stats at the very end when we have handled infections. So yeah, let's see. I think we'll call it after we have done. So here we are in the run. So we will call it on the next day. So when we have looped through our simulation, we will update stats. Or actually, no. We will do it. We will do it at the end of handle infections, because that's like the conclusion of that day. So self.update stats, and we give it the day, right? And right now that only prints the line. So let's do that. Yeah, did we do print or did we do print line there? Just did print. So of course this is no longer compatible with the day printout that we did, so this is going to be a mess. But we just want to see if the numbers go up, and they don't. Or do they? Okay, so the first one is susceptible, infected, and recovered. So no, that is not good. So we don't have any. Nothing is dynamic in our simulation here. So the threads throughout the days, day 158, and the threads have. All the threads have an equal number of people. They have 0 infected, and they have should have 1 person recovered. Let's go up to the first day. Because it seems like, yeah, of course, the seeding algorithm is actually not correct, is it? Because we need to loop multiple rounds, but we can ignore that for now, because we are seeding an individual that are infected in the simulation, and that, as you can see here, it says 16 blah blah, and it says 1 and 0. That means that there is these numbers are susceptible, this person is infected, and this is the people recovered, and then that person recovers in each thread. But that person does not infect other people, so we are missing something that makes that happen. Okay, so we need to see what happens in our okay, so when we do run, then we do next day. We go down here to next day, and then we say what happens if the person is. Okay, so we loop through the list of people. If on the current day this person is infected, if the person is not infected, then we return. We know that there is an individual that is infected. We can check this, because we can do this. We can put a breakpoint there. Oh, wrong one. Oh, I pushed the wrong one there. Yep. Because we never get to the point in the code. Okay, let's go back down again. We never get to this. Do we get to this point in the code? Yes, absolutely. We have a person here who's not infected on the current day. Very interesting that it doesn't say person here. even though we are inside this loop, right? That is also strange. Okay, so if the person, probably the person actually went out of scope here because the person is no longer needed. And that is okay. Okay, so when we get to this point, we did find, let's see if this, do we ever get here? No, we never get there. So if we do put a print line here, hey, scroll up there. Do we get there to the end of this clause? I assume so. We don't get to the end of the clause. Does this mean that there is no one in the system that is infected at this point? But we do count them as infected when we count the state. So why would that be? That is strange. And why doesn't it print? Why doesn't it print hey when we add it here? That must mean, yeah, it means that it never gets there, right? So no one on no days return that their state is infected. Nobody on the current day is listed as infected, even though we are looping through multiple days. Go here again, day 0. Condition, we can say is a day bigger than 10. Now we are on day 11, yeah. So on day 11, and I guess we still don't come anywhere there. Okay, so this is probably something that's relatively easy to solve. There's probably some kind of logic error in the way this works. One thing we should do is we should probably inspect the workers, see if they have an infected person. I think that is probably important, just to make sure that that works. So what we can do is we can come here to create infections, and we can see if that ever happens. Does it ever create an infection in person? And I do believe that it does. So it did here. And where are we in the stack? So we are in handle infections, and we got an ID, and we are now creating that, and then we can go here. Let's see. Continue. No. We never get there. Yeah, we do. So we have now with this person that we are looking at, which is here. We have mutated that person. The person does not have a clinical course. No, it's because that's the last thing we are setting. Can we evaluate this expression? Evaluate expression. Able to create. Okay, so we cannot evaluate that expression in here. And unfortunately I cannot break it there, but I can, again, we can add a print line here to just so that we can catch this and see what's going on. Clinical course, yeah, so we do have a sick day array. And the person gets infected on day 0. So we can try to evaluate an expression here. We can say person dot get status on day. And what happens if you get the status on day 1? Variable not found. That is okay. Let's just add let's test equals person dot get status on day, and we get status on day 2. I just want to see that I'm going to see that variable. Okay, so that person is affected, yeah, so that works. What if it's day 1? So we can actually do, we will do test 1, 2, 3, 1, 2, 3, 4. Then we'll ask for day 1, 2, 3, 4. And I want to see whether the person on the 4th day, where's test 4? Where's test 4? None. What about test 3? 3 is some, yeah, so the person on that day infects someone, and that is this ID. Okay. So we know now that that works. We know that, or at least we know that the generation is correct. Then here we need to see if they ever send infections. No, they never send infections. We never get to this point. Okay, so there is something wrong there. Yeah, okay. If the current day has, the current sick day is infect, then it should call this function. But it never does. That is a mystery. Okay. Let's just do one moment of troubleshooting, and if I can't finish this now, then unfortunately I will have to end this stream shortly because I have some other work to do as well. But let's try and logically go through and see if there's any good reason why this fails. So for each person in self people, we know now that some of these should be infected, right? That is the last thing we do know. Our problem is that we never get down here, even though there are infected. So why does this fail? Why does current day? When we ran this, earlier, we did see that some of the people were indeed infected, and that on a certain day they said that they were infecting someone. So why is it not working for us right now? So we should It is strange that it doesn't find anyone in this array that is not infected here. That does not make sense. So we are, I assume that we are passing days in here. One thing we can do is that we can check, just to make sure, we can make sure that we infect the first person in the seeding round. We will infect we will also send, sorry, messed it up a little bit there. We'll say in the seeding round, we will also infect the first person in the worker range. Then when we look at the worker range, we'll know that it's something there. Let's just run this and see that it works. No, that panics. And we do +1. Okay, this is interesting too. Yeah, so that works. So now we have infected. We know that the first person in each worker's round should be infected. So if we stop the worker, we can stop the worker anywhere. We can stop it here. Well, no, we cannot. We can stop it here on a day after a certain day. So we can stop it, say, here. We can make this. We can say we want to wait 5 days. Then we stop it. It's a conditional breakpoint. So on day 6, we can have a look in self, and we can see if the second or first person here is in fact infected. No, that one is not infected. What about this one? Yeah. This person was infected on day 0. And the person has a clinical course. On this day it infects, on this day it doesn't infect anyone. It's almost like that our comparison doesn't work. We know that they seed correctly. Almost like this fails for whatever reason. And we add a conditional breakpoint that says like current day dot 0 equals state infected. I think that would probably not work because then we're doing the same thing, right? If we add an else here with something in it, now we're grasping at straws, right? So we do that. Should be saying hey quite a lot, but didn't. But it could pass by so quickly that we can't see it. Again, the comparison fails, right? Okay, so this is probably some kind of stupid error, right? Okay, so we'll stop it there and we'll have a look. We'll inspect self and we see self.people, and in fact we have one here. No. These have no infections, that is correct. Let's do one more tick. Okay, so self people. Okay, so these people are also not infected. So it is true that when we get here to this point, these people are not infected. Are we? Yeah, we're definitely messing something up here because right now these this array of people. So it's almost like we run this before we run the seeding. Do we do that? When do we do the seeding? So we are actually starting the workers before we are doing the seeding, but they should wait. But we can do the seeding before we start the workers. Still, we have the same situation that the people are moving from infected to recovered, but they're not infecting other people. Sim worker, and then we go next day. Now, yeah, that is only one. Next day. The people are passing through this state, but they never. Yeah, so the problem is that somehow in this area here we are not succeeding. Just gonna do a shot in the wild here and restore these. Restore this particular iterator that we had before. Of course, it doesn't change anything because it does the same thing. So there's some kind of logic error here that gets that becomes problematic. And self is of course, yeah, is this one, and we should. But it's also very suspicious that we put the one in the range, right? To put that one on the lower end of the range, we put that person to be infected. This person does not infect anyone, this one doesn't infect anyone, and this one doesn't infect anyone. Yeah. Big mystery. Is it because we don't clear that channel every time we loop it around? It also seems like all of the, because of the numbers that are coming out at the end, it does seem like we have indeed, like if we go to update stats, sorry. Then we do have 2 infected people in the simulation. On day 0. So we do know at least that this iterator finds those people. We can because this messes up, we can try to use that iterator to get people out. Then we will, yeah, so we can do let infected equals, and we take that iterator. We don't actually count, we just get the iterator. If you're allowed to do that. So status is that state dot infected. This iterator should give us all the infected people, so we can do, instead of in self people, we can do infected. Okay, so now we got a panic. Interesting. So this somehow yielded us a panic. Okay, so now we are getting somewhere. We're getting, okay, so then look at that, with that iterator instead of the other one, it did succeed. Why is this comparison failing? State infected. We are doing the same thing, but when we did this, it works, but on the other one it doesn't. Right? Or am I just missing? Now we have one more version here. Or am I just missing the early messages here? So it does initially, it does find some people and just not seeing it. Do run it again. Very, very top. Do we get the printout? Okay, so that is really the mystery of the day, isn't it? I think we will perhaps have to end on this mystery now because time is running away from us. But in this, why would this if condition fail us while this condition, this loop, this iterator here that filters on self people iter? Why would that work? Is it because what is current day? Can we get some more information about this one? When we looped with the iterator, that really worked, didn't it? And then it got into some other errors that are probably hidden from us now because we're not successfully running this this loop. So we are still on self people. This we're not allowed to do because then we're moving the person out and self.people. I'm gonna stop it here. Let's see, just have one last look at current day. This is for Tuple, and the first one is epimodel.susceptible. And do it one more jump, current day, and the first one is susceptible. Yes, all of them are susceptible. Okay, so I have to confess that I have absolutely no idea why this does not work. Problem is quite simply that if the comparison doesn't appear to function, and I see no reason why that is. We can try to swap this around. The only thing that we do is we include everyone that is infected in this one. So we can say if current day is infected, then we don't do anything. Else we return. It should amount to the same thing. So of course that didn't do anything. We can try one more time just to pick out the state directly. We can say state equals current day dot 0. But there is really no way why this would not function. So we can then go state equals like that. And we have exactly the same situation. So the problem, so to conclude, if we use this iterator expression up here, where we loop through, we do for person in infected, that yields us a person reference. Or a borrow of this person, so we borrow this person for each iteration. So if we do this, then yeah, we do run, we do get some crashes, but that's okay. It crashes because I assume because there are errors in here. It runs several times and then it panics here because it cannot find the correct person ID. So there is some logic error that we have in our code here. The problem is that this so the way this iterator is constructed is that it basically says p person dot get, it checks for this. If the status on the day is that state infected, then we do something. But if we put something, but when we instead of doing this in the iterator, we just loop through the array, we get the same thing. But it doesn't. This comparison doesn't work. That is really, really strange. I don't understand why that would be. I don't understand that at all. It cannot be that this is a borrow, can it? We can try to match on state. And then if it's infected, we can just print something. That we are aware that it happened. Actually, we don't need to print these other ones because we're only interested in this one. We can try this. Because this gave us the same error. It crashes on line 274. If it's susceptible, we want it to return. And if the person is recovered, we want it to return. If not, it says inf. So okay, so this might not have changed anything. No, so it hasn't changed anything. Okay, I think I'm gonna have to stop the stream there because now it's getting late. We've been streaming for over 2.5 hours. I think I'm a bit surprised by this ending here because I really thought that this would function. I think we have gotten the threading and the communication correctly. something happens here, and I'm super surprised that this does not work, that the iterator functions, but that the filtering down here doesn't work. I'm gonna have to try to recreate this with a minimal example so that we can see, try to understand why this problem arises. I don't think I have time to do that today, but I will need to investigate this one a little bit, because this is behavior that I would not expect at all. Basically because the iterator triggers on a specific, the iterator works so that the filtering with the expression of the current day.0 equals state dash colon infection works in the iterator, but it doesn't work in the if clause, and it is the same collection, right? That is very, very strange, and I'm super surprised to see this. Yeah, need to try a minimal example here and see if there's something weird going on, or there's probably, like, there's always some error happening that you don't expect when you're learning something, some behavior that you didn't know about. But this is really strange, and I'm very curious to understand what behavior of the language would trigger the thing that we're looking at here. Is it some type conversion? Is it like the fact that state, it says here that state is a copy type, right? So yeah, maybe there's something there. Maybe we are somehow, it's a matter of borrowing it, but why would that matter, right? Why like this? Why would this do anything? It didn't. Yeah. So the problem again is that this expression here in the iterator filter, that works just fine. But down here, when we do exactly the same thing, it doesn't work. Actually, just as one last thing, we will take this thing out of this expression and we'll check it in here. We'll do person. And then do if the person is, so if this expression works down here, then we will print line it works. Wait. Yeah, so the reason we're failing now is because it falls true to this point. Okay, so that did work. Did catch this here, but let's have a look and see what is current day. No, that is still a mystery. When we ask for get status on the day in this way, it works. But when we get the current day out into this variable, we can look at current day here, yeah. So when we call person.getStatus on day and we compare the result here with infected, we get it does work. But on the other hand, up here, so let's do exactly, remove this, and then we do exactly the same, but we say, instead of calling it, we say it's current day like this, .0. Works, it works. Let's see which one of these triggers first. So this should be the same thing, right? And it triggers. Just a moment ago, we didn't get this to work. Okay, so what if, yeah, so, okay, so then that works, right? So else, we can do return, right? Whoa. When I added the return, the breakpoint no longer fires. Why is that happening? Is this a debugger problem? Like, can't it? We can see if this this operates now, but we should, if this is the case, we should fire this thread at this point here again. Oh, look at that! So now we are getting. Now we're not getting it. Now it is falling through. This is really strange. I wonder if it has something to do with the optimizations. Or where things go out of scope, right? Let's try this one more time, this behavior. So what we're looking at is we're getting this current day, and then we are having, now it works. If I put an else here, and we put a return in there, does it work then? No, then this never fires. But why would this be omitted? That completely does not make sense. So this appears to only work if there's no code afterwards. Okay, so now we didn't do it again. So now there we are. Okay, this is a mystery behavior, and I really think this one is very strange. But I need to dig a little bit into this one, like I said. But there's no reason why adding an else clause here would cause this to trigger. So this is really mysterious. Okay, I think I'm gonna have to ask some people for assistance on figuring this one out. So anyway, okay, but thank you for watching the stream. Sorry we didn't manage to get through part 2 and successfully get the simulation running. But we did learn some things, and we did check in on channels working well, and we have modified the code quite a lot. I suspect that next time we will get this running. We just have to figure out what is going on here, and if this is something weird with the debugging, or with something weird in the way the binaries are compiled. But it is super strange that adding an else clause would make this breakpoint trigger when literally it doesn't really do anything. If anything, you would expect that if there was more code after, this would not be optimized away in some way or whatever. Yeah, this is awkward. Okay, that's it for now. Thank you for watching. I will be back at a later point. Probably not before in a couple of days, but hopefully next time I'll have some answers to this particular question. Bye.